Now let's look at some examples. The first example, it's trivial but important. Let's take J to be 0. Okay. So what are the possible values of M then? Hello? If J is 0, what are the possible values of M? Can you guys hear me?
Yeah, I'm thinking.
Yeah, do think, please. Here's the list.
Wait, then minus j is also 0.
Yeah,
It's 0, 1, and -1.
no, it's just 0. Right? Because in that case, if J is 0, this is 0, 0 minus, and then you go to -0, which is also 0. So there's all these things in between, they collapse to just one thing, 0, right?
Oh,
Okay, good. Anyway, so this may seem trivial, but it's actually important. Then what is the dimension of this E-rep? What is the dimension of this E-rep?
1.
Exactly. So how do we label that vector? J is 0, M is 0, right? So what are the matrices then? So the matrices will be 1 by 1, right? Because we have only one dimensional. The matrices of the representation will be 1 by 1, right?
Yeah.
There'll be numbers. Okay, now if I want to find J3, what I have to do is I have to sandwich it between the vector and its conjugate. This is 0, right? And what about J plus minus? So if I use, since this is the maximal weight state, this is also going to be 0. So all in this representation, J3, J plus, J minus, they are all 0. Okay. And therefore the group elements, which are given by e to the power I something 0, all the group elements are just the number 1. So this is a trivial representation, right? We call it a trivial representation, where all the elements of the group map to only the identity element. So this has application. This is application in physics, in quantum mechanics. Spin 0 particles, which are known as scalar particles, okay, they form this they form this representation, okay, this representation of SU2. Even the trivial one is important. Okay. Okay. Now let's look at the next case where J is half. Okay, what are the possible values of M now? What is the highest value of M? What is the highest possible value of M?
Half.
Right. And then we should go one step down. Then the lowest, the next lower value should be
Minus half.
minus half. But we know that the highest value should be minus the lowest value and vice versa, right? So there should not be any more, right? So the dimension of this representation will be how many?
2.
Yeah. Okay, now we are in an interesting territory. So let me just write out these equations again for reference because we will need them. Okay, so let me just copy, these equations and write them out here so we can have them handy because we are now going to be using them. Okay, I'm just gonna minimize them a little bit. Okay, so let's look at the basis states. So the basis states, there would be two vectors. The first vector is half, half. The second vector is half minus half. So this I'm just gonna call, say, half. And this I'm just gonna call minus half, right? Because this thing is the same. So now let's work out what J3 is. So J3 is going to be a matrix, so whose first row is labeled by one state. So this would be the first element of J3. The second, column, we are looking at the first row here. So that's labeled by one of the states. The column is labeled by the ket. So here, if you're looking at the next row, it'll be minus half J3, the same column. So this and this are the same. And here we'll have minus half J3 minus half. Okay, so this is going to be the matrix representation of J3 in this representation. Now we have to calculate this. It's very easy to do. J3 acting on this is going to give me the eigenvalue, right? The M3 eigenvalue is half. So we get half, and then I get the inner product of half and half, which is 1. Right? I can just, instead of writing this, I can just write 1 here. Now this thing is going to give me minus half, and then I'm going to have half inner product with minus half. But from orthogonality, what is the value of this thing?
0.
Yeah. So the off-diagonal element, this off-diagonal element is 0. Similarly, here we get plus half, but what's left over are two states which are orthogonal to each other. So we get, just 1 second. Okay. So here we are going to have J3 acting on this guy is going to give me minus half and then normalization, right? So we see that in this representation, J3 is just sigma 3 by 2. Okay. Now let's figure out J plus. So J plus similarly is going to be, there's half J plus half, half J plus minus half, minus half J plus half, minus half J plus minus half. Okay. Now here, J plus acting on this is going to give me something proportional to minus half, right? Right? which will be orthogonal to this thing. So this thing is going to give me 0. Sorry.
Shouldn't J plus increase the number?
You're right, I misspoke. J plus would just kill this guy. So this would be 0. Yeah. So similarly, this will also give me 0 because J plus acting on plus half is just give me 0. But here, when J plus acts, I will get half, half, and a constant. And if you calculate that constant, you will see that it's just going to be 1. Okay, so because if I look at here, if I look at this guy, and I'm using J plus on M equals to half, where J is half. So M is minus half, sorry. So if M is minus half, J is plus half, then this becomes plus half, right? So this becomes 1. And here we have J plus half, M minus half, so this becomes 0. So there's a 1 left over. So this whole thing becomes 1. So using this, we get over here, we just get plus 1. Okay, here we get again J plus half here, which of course the inner product with this will give me 0. So the representation of J plus is going to be this. Okay. And similarly, if you now work out what J minus is, you see that it's going to be 0, 0, 1, 1, 0. And you can then, okay, say what is J1? Well, J1 is half of J plus plus J minus. And this is easy to see that this is just this, which is sigma 1 by 2. And J2 is going to be 1 over 2i, J plus minus J minus. And if you work this out, you get a factor of half, 0 minus I 0, which is sigma 2 by 2. Okay. So we see that we regain the fundamental or the defining representation of SU2, right? Which is what we should get. So, and then you can say, okay, what is J1? And you can figure that out yourself. You can even write a computer code, which will take a given value of J1 and use those magical formulas and spit out what the representations are. And then, once you have these matrices, it's easy to see that half is nothing but 1, 0, up to some normalization constant, which we choose to be plus 1, some phase, and minus half is then 0, 1, because these are the eigenvalues of the J operator with eigenvalues plus half and minus half.